and planets, each holding mysteries that are both captivating and unsettling. Beyond the familiar glow of our sun lie places in the universe that defy imagination, resembling more nightmares than reality. Picture worlds where rain is composed of sharp glass fragments, perpetual darkness shrouds the skies, or surfaces bubble with seething molten lava. These are not serene, dreamlike planets. They are the most daunting in the cosmos, where conditions are so severe that conventional life forms could not endure. The goal of this documentary is to push the boundaries of your understanding of the universe. Each planet we encounter will reveal the profound strangeness and terror that can exist in space. HD 189733b is a planet located 64.5 light-years away in the constellation Vulpecula. Known as a hot Jupiter due to its size and proximity to its star, it boasts extreme atmospheric conditions that challenge our understanding. One of its most striking features is its unique phenomenon of glass rain, which, despite sounding like science fiction, is scientifically verified. The planet's atmosphere is a turbulent inferno with temperatures surpassing 1,000 degrees Celsius, 1,832 degrees Fahrenheit, a result of its close orbit around its host star, subjecting it to intense stellar radiation. In this blazing environment, silicate particles are formed and remain molten in the atmosphere due to the extreme heat. Wind speeds on HD 189733b paint a dramatic contrast to Earth's weather systems. While hurricanes on our planet can reach speeds up to 250 kilometers per hour, 155 miles per hour, the winds on HD 189733b exceed a mind-boggling 7,000 kilometers per hour, 4,350 miles per hour, almost 20 times faster than Earth's most powerful hurricanes. To put this in perspective, these winds could cross the continental United States in less than 2 hours. These extreme conditions make HD 189733b a fascinating study, offering insights into planetary atmospheres and the astonishing forces at play beyond our solar system. The extraordinary wind speeds on HD 189733b are driven by the planet's close proximity to its star, which creates intense temperature differences across its atmosphere. This thermal imbalance propels hot air at tremendous speeds towards cooler regions, a phenomenon that defies comparison with anything on Earth. On this distant world, wind isn't just atmospheric movement. It shapes the planet's weather patterns and plays a crucial role in the surreal occurrence known as glass rain. Glass rain on HD 189733b is both fascinating and violent, profoundly influencing the planet's environment. Unlike Earth's gentle rains that nurture life, here molten silicate particles caught in the planet's fierce winds solidify into shards that pummel the surface at speeds up to 7,000 kilometers per hour, matching the velocity of the winds themselves. This relentless bombardment sculpts the planet's rugged terrain over vast timescales, potentially forming expansive, reflective dunes that glisten eerily under the nearby star's light. The implications of glass rain extend beyond physical surface alteration. The energy dynamics of this environment, fueled by the star's heat and kinetic energy from falling glass, sustain a volatile atmosphere unsuitable for liquid water, the cornerstone of life as we understand it. These extreme conditions pose significant challenges for identifying stable habitable zones on HD 189733b. TRES 2b, an intriguing exoplanet located approximately 750 light-years away from Earth, holds the distinction of being the darkest planet known in the universe. This distant world reflects less than 1% of the sunlight it receives, making it darker than coal and a captivating subject for astronomers and scientists alike. The extreme darkness of TRES 2b is primarily due to its unique atmospheric composition and chemical processes, features that sharply contrast with the planets in our solar system. Its atmosphere is rich in light-absorbing chemicals such as vaporized sodium, potassium, and titanium oxide. Unlike in our solar system, where titanium oxide can reflect light and enhance brightness, the atmospheric conditions on TRES 2b prevent such reflection. Instead, these chemicals efficiently absorb almost all incoming sunlight, trapping it as heat and preventing any significant light reflection back into space. Additionally, There are indications that unidentified compounds in TRES-2b's atmosphere contribute to its high level of light absorption. Scientists continue to investigate the exact nature of these compounds. The planet's scorching temperatures, which can soar to around 1,000 degrees Celsius, 1,832 degrees Fahrenheit, also aid in maintaining its dark appearance by promoting chemical reactions that favor light absorption over reflection. The atmosphere of TRES-2b is believed to be rich in vaporized sodium and potassium, both known for their ability to absorb visible light. In the extreme heat of TRES-2b's environment, these elements prevent sunlight from being reflected back into space, contributing significantly to the planet's profound darkness. Additionally, titanium oxide, typically a light reflector in planetary atmospheres under the extreme conditions of TRES-2b, likely absorbs light instead of reflecting it, further intensifying the planet's dim appearance. Researchers also speculate about the presence of unidentified compounds in TRES-2b's atmosphere. These mysterious substances are thought to enhance the planet's light-absorbing capabilities, potentially revealing novel chemical processes occurring under the extreme temperatures and pressures unique to exoplanetary atmospheres. Kepler-70b, an exoplanet known for its extreme heat, challenges our understanding of planetary climates with its remarkable temperature range. Orbiting very close to its host star, Kepler-70, this planet experiences temperatures far surpassing those found on Earth or most other planets. Temperatures on Kepler-70b can range between 6,700 and 7,300 degrees Celsius, placing it among the hottest planets ever discovered. Its surface conditions resemble those found on the outer layers of stars rather than typical planetary atmospheres. The intense heat on Kepler-70b is primarily caused by its extremely close orbit around Kepler-70. This proximity exposes the planet to intense levels of stellar radiation, heating its surface to temperatures that vaporize metals and rock. This creates an environment that is incredibly harsh and almost unimaginably hot. Due to its tight orbit, Kepler-70b does not experience distinct day and night cycles, resulting in uniform temperatures across its surface that approach the limits of what solid matter can withstand before turning into plasma. Moving beyond the extreme temperatures of Kepler-70b, it is important to understand how its close proximity to its star profoundly influences its surface characteristics. The planet's surface is drastically different from any on Earth due to the intense stellar radiation it receives. This close relationship with Kepler-70 causes Kepler-70b's surface to reach temperatures where metals and rocks not only melt, but vaporize, creating a landscape that is constantly changing. During its orbit, the extreme heat can form pools of liquid metals and silicates on the planet's surface, giving it a reflective appearance that contrasts sharply with Earth's familiar rocky or water-covered surfaces. The gravitational forces from its close orbit also subject Kepler-70b to significant tidal stresses, potentially leading to volcanic activity and unusual geological formations. This continuous activity contributes to a dynamic and ever-evolving world where even the ground beneath one's feet, if it were possible to stand there, is as transient as the atmosphere above. Kepler-70b's extreme conditions provide a profound example of the varied environments planets can endure. This diversity offers valuable insights into the processes governing planet formation and survival across the universe. For centuries, scientists have been fascinated by the intricate factors influencing planet formation, such as the composition of protoplanetary disks, distance from the host star, and the star's specific characteristics. Kepler-70b's existence in such an inhospitable region close to its star challenges established models of planet formation. It suggests that planets can form and maintain stability even in environments typically considered too extreme for such processes. This resilience hints that the mechanisms behind planet formation might be more adaptable and resilient than previously understood, capable of producing stable celestial bodies despite intense thermal and gravitational pressures. Studying Kepler-70b's extreme conditions also provides valuable insights into the later stages of planetary systems. As stars evolve and expand into their red giant phase, They can engulf their innermost planets, subjecting them to conditions akin to those experienced by Kepler-70b. This phenomenon underscores the dynamic nature of planetary systems and offers a glimpse into the fate of planets as their parent stars progress through their life cycles. Planet GJ 1214b, located about 40 light-years away, introduces a phenomenon that challenges our understanding of water in extreme environments. Classified as a super-Earth due to its size falling between Earth and gas giants, GJ 1214b hosts conditions leading to what's known as burning ice. This term describes a state of water existing under immense pressure and temperature conditions on the planet, conditions so extreme that they blur the boundaries between solid, liquid, and gas phases as we know them on Earth. The concept of burning ice on GJ 1214b arises from its dense atmosphere and potentially deep oceans. Under such high atmospheric pressure, water transforms into a supercritical fluid, a phase combining liquid-like properties such as solvent capabilities with gas-like behaviors such as filling containers uniformly. This supercritical water isn't ice in the traditional sense, nor does it burn in a fiery manner, but its existence under such extreme circumstances justifies the term. Burning ice. The planet's temperatures also play a crucial role in this phenomenon. Though not as searingly hot as some other exoplanets, GJ 1214b's temperatures are sufficient to prevent water from existing in a familiar liquid state at its surface, thereby fostering this exotic supercritical phase. This creates an environment where water behaves in ways entirely unlike anything observed on Earth, capable of dissolving materials like a liquid while freely moving and filling spaces like a gas. The pressure on GJ 1214b stands in stark contrast to the immense pressures found in Earth's deepest oceans, challenging our understanding of extreme environments. Earth's oceans reach their greatest depths in the Mariana Trench, where pressure reaches approximately 1,086 bars, or 15,750 pounds per square inch, psi. This pressure is akin to an elephant standing on a postage stamp, highlighting the intense conditions at such depths. However, GJ 1214b presents an entirely different level of pressure intensity. The planet's atmosphere is estimated to exert pressures thousands of times greater than the deepest ocean trench due to its larger mass, high density, and dense atmosphere, likely composed of heavy molecules. Under such extreme conditions, substances like water can exist in exotic states such as supercritical fluids, blurring the line between gases and liquids. Studying GJ 1214b poses unique challenges for scientists due to its intriguing characteristics and distant location. Situated about 40 light-years away, this exoplanet demands advanced telescopes equipped with highly sensitive instruments to analyze its atmospheric composition, temperature, and other critical features. Technological limitations and the vast distance from Earth complicate our efforts to gather and interpret data from such remote celestial bodies. Another significant challenge lies in the capabilities of current astronomical instruments. Despite considerable technological progress enabling us to observe distant planets more effectively, there are still constraints in resolving the intricate details of exoplanetary atmospheres. Specifically, identifying specific molecules or grasping the dynamics of atmospheric conditions remains challenging. This difficulty is exacerbated by the interference caused by the intense brightness of host stars, which often obscures or dilutes the signals emitted by these planets. This makes it challenging to extract precise characteristics of the planet from the mixed signals of reflected and emitted light. Furthermore, interpreting data from GJ 1214b is complicated by our limited understanding of how materials like supercritical fluids behave under the extreme pressures and temperatures found on such distant planets. Scientists heavily rely on theoretical models and laboratory experiments to simulate these conditions. However, these models have inherent limitations and cannot perfectly replicate the complex environments of exoplanets like GJ 1214b. Consequently, ongoing efforts are focused on refining these models and developing new techniques to enhance our understanding of the data gathered from observations of this intriguing exoplanet. WASP-12b, located about 600 light-years from Earth, has earned the moniker Doomed Planet due to its exceptionally close orbit around its host star, a fate that has captured the interest of scientists and the public alike. This gas giant, comparable in size to Jupiter, is gradually being engulfed by its star, a dramatic example of the powerful forces shaping planetary destinies. The main reason for WASP-12b's doomed status stems from its extremely close proximity to WASP-12, its host star. This proximity subjects the planet to intense gravitational forces, resulting in it becoming tidally locked. This means one side of the planet always faces the star, while the other remains in perpetual darkness. The sun-facing side of WASP-12b experiences blistering temperatures exceeding 2,500 degrees Celsius, about 4,532 degrees Fahrenheit, causing its atmosphere to be stripped away into space. The star's gravitational pull has deformed WASP-12b into an elongated, egg-like shape, rather than the spherical shape typical of planets. This distortion vividly illustrates the star's profound influence on the planet. Observations reveal that WASP-12b is losing a substantial amount of mass, approximately 189 quadrillion tons per year, due to the star's heat and gravitational forces stripping away its outer layers, a phenomenon known as atmospheric escape. Scientists estimate that within a relatively short astronomical timeframe, possibly around 10 million years, WASP-12b may be completely consumed by its host star. This inevitability underscores the planet's doomed fate and underscores the dynamic and often violent nature of planetary systems. The study of WASP-12b and its inevitable demise provides profound insights into the planetary life cycle, particularly for planets in close orbits around their stars, showcasing the immense forces at work in our universe. Observations of WASP-12b's spiral towards its host star offer a captivating and somewhat foreboding view into celestial mechanics at their most extreme. Utilizing advanced telescopes and space-based observatories, astronomers have collected crucial data on this doomed planet, shedding light on the process of its consumption by the star. Astronomers have made compelling discoveries, notably detecting a vast cloud of material being drawn from WASP-12b towards its star due to the planet's close orbit and powerful gravitational forces. This material forms an extended atmosphere or exosphere stretching from the planet towards the star, creating a bridge of gas gradually siphoned off WASP-12b. Spectroscopic analysis, a method to determine celestial object compositions by studying emitted or absorbed light, has played a pivotal role. Through spectroscopy, scientists have identified hydrogen, helium, and heavier elements among the gases in this stream, stripped from WASP-12b's atmosphere and assimilated into the star. Further observations reveal the staggering rate of mass loss, distorting WASP-12b's shape under the star's tidal forces into an elongated form. This distortion not only disrupts the planet's gravitational balance, but also accelerates atmospheric escape, hastening its demise. As WASP-12b sheds mass to its star, significant changes occur in its atmosphere, with substantial quantities of gases, including hydrogen, helium, and heavier compounds, stripped away. The gradual stripping of WASP-12b's atmosphere leads to a reduction in atmospheric pressure, altering the delicate balance between the planet's surface and the vacuum of space. Enhanced by the intense heat from its nearby star, the remaining atmosphere expands and escapes more readily, hastening the loss. This atmospheric depletion can thin the protective layer around the planet, exposing its surface to harmful stellar radiation, potentially raising surface temperatures and even affecting the chemical composition of the surface itself. Additionally, the star's tidal forces elongate WASP-12b and can trigger geological activities like volcanic eruptions by heating the planet's interior. This geothermal activity might reshape the planet's surface over time, carving new features or altering existing ones. Studying WASP-12b's gradual demise not only provides insights into its inevitable fate, but also offers broader implications for understanding planetary evolution and the intricate interactions between stars and planets. These observations challenge previous assumptions about planetary orbit stability and the factors influencing planetary destruction. Transitioning from the dramatic case of WASP-12b, we encounter the intriguing scenario of HD 116906b, an exoplanet located approximately 300 light-years away from Earth. This planet's highly eccentric and distant orbit around its host star presents a stark departure from typical planetary systems. Positioned at a remarkable distance exceeding 650 times that between Earth and the Sun, HD 106906b resides in a region where traditional models of planet formation and orbital mechanics struggle to provide clear explanations. The disrupted orbit of HD 106906b prompts questions about the mechanisms that could have led to such an unconventional path. One prevailing theory suggests that gravitational interactions with other planets within its system, or possibly a passing star, could have profoundly altered its trajectory. Such interactions would need to be precisely orchestrated to place HD 106906b in its current orbit without ejecting it from the system or causing a collision with its host star. Another intriguing aspect of HD 106906b's orbit is its significant inclination relative to the plane of its solar system. This tilt adds to the mystery surrounding its origin and evolution, hinting at a potentially turbulent history within its planetary neighborhood that remains incompletely understood. The peculiar orbit of HD 106906b not only captures the interest of astronomers, but also challenges existing theories of planetary system formation. Traditional models focus on protoplanetary disks, dense gas and dust disks around young stars, as the cradle for planet formation, predicting planets to form within the disk and maintain orbits close to its plane, akin to our own solar system. However, the unique characteristics of HD 106906b suggest alternative mechanisms may influence the formation and evolution of planets in ways not fully accounted for by current models. One of the primary puzzles posed by HD 106906b's orbit is explaining how a planet ended up in such a wide and inclined trajectory, contrary to predictions from traditional formation mechanisms. This discrepancy suggests that additional factors beyond standard accretion and disk dynamics played significant roles. Theories propose scenarios involving gravitational disturbances from other massive bodies within the planetary system, such as giant planets, or close encounters with passing stars that could drastically alter a planet's path. These ideas imply a more tumultuous and dynamic early environment for the solar system than previously imagined. Moreover, the existence of HD 106906b challenges established notions about achieving and maintaining stable planetary orbits. Its current path indicates a potentially complex migratory history, possibly involving processes like planet-planet scattering or capture from another system. These mechanisms may contribute to the diversity of exoplanetary systems observed, extending beyond the orderly patterns found in our own solar system, expanding on the exploration of HD 106906b's unconventional orbit and its implications for traditional theories of planetary formation. We explore speculative yet intriguing possibilities for what may have shaped this exoplanet's extraordinary orbital characteristics. Unlike the familiar patterns seen in our solar system, HD 106906b's orbit suggests a backstory rich with celestial dynamics that challenge our understanding. A compelling hypothesis suggests that HD 106906b's orbit was influenced by gravitational interactions with another unseen companion within its system, potentially another planet or a brown dwarf. These interactions could have profoundly redirected HD 106906b early in the system's history, sending it into a distant and inclined orbit. This scenario hinges on a delicate balance of forces, ensuring that HD 106906b settled into its current wide orbit rather than being ejected entirely from the system. Another perspective on HD 106906b's perplexing orbit explores the possibility of a close encounter with a passing star during the early stages of its planetary system. This scenario suggests that within the dense environment of a star cluster, where stellar interactions are frequent, the gravitational influence of a nearby star could have profoundly disrupted HD 106906b's trajectory. Such an encounter could have altered the planet's velocity and direction, setting it on its current unusual path. Furthermore, the dynamics within the HD 106906 system itself during its formative years may provide additional insights into the origins of the planet's peculiar orbit. The phenomenon known as planet-planet scattering is proposed as a plausible mechanism. This process involves gravitational interactions among young planets within a forming system where planets can fling each other into different orbits. In the case of HD 106906b, planet-planet scattering could have propelled it into the wide and highly inclined orbit observed today. CoRoT 7b is an exoplanet situated 489 light-years away in the Monoceros constellation. What makes this planet particularly intriguing is its extreme environmental conditions, akin to rock showers. Orbiting its host star at a distance 23 times closer than Mercury orbits the Sun, CoRoT 7b experiences scorching temperatures on its dayside, reaching up to 2,500 degrees Celsius, 4,532 degrees Fahrenheit. Such intense heat causes rocks on its surface not just to melt, but to vaporize into gas, a phenomenon unseen on Earth. This vaporized rock is carried by the planet's atmosphere to its cooler night side, where temperatures drop significantly. Here, the rock vapor condenses into particles that eventually fall back as precipitation. This precipitation, however, isn't water but actual rock particles, a unique feature of CoRoT 7b. This cycle of vaporization and precipitation is a constant process driven by the stark temperature contrast between the planet's day and night sides. Additionally, CoRoT 7b's close proximity to its star causes intense gravitational forces that not only distort the planet's shape, but also affect its internal heating and atmospheric circulation. These forces contribute to the complex weather patterns observed on the planet, adding further intrigue to its study. The atmospheric phenomena observed on CoRoT 7b provide a unique glimpse into conditions vastly different from those found on Earth or within our solar system. On the planet's scorching dayside, where temperatures reach up to 2,500 degrees Celsius, rocks vaporize into gas, which then cools and condenses on the cooler night side, forming rock rain. This extraordinary cycle offers scientists a live laboratory to study mineral and rock behavior under extreme conditions that cannot be replicated in terrestrial environments. Understanding how materials vaporize and condense on CoRoT 7b is crucial for refining models of planetary formation and evolution. These insights extend beyond exoplanets, potentially shedding light on Earth's geological history, atmospheric formation, and crust development. Moreover, studying CoRoT 7b's atmospheric dynamics helps scientists explore how extreme temperature gradients influence weather patterns and climate across different planetary settings, from scorching exoplanets to those more akin to Earth. This research challenges current theories about planetary habitability and expands our understanding of conditions that could support life elsewhere in the universe. By enhancing our knowledge of planetary diversity and evolution, researchers can better identify potentially habitable exoplanets and prioritize targets for future exploration. Scientists have been fascinated by 55 Cancri e, an exoplanet located 40 light-years away in the Cancer constellation and about twice the size of Earth, primarily because of its intriguing potential. It may possess a surface abundant in diamonds. This hypothesis arises from the planet's unique composition and the extreme pressure conditions it sustains. Unlike Earth, which has a rocky surface, 55 Cancri e is predominantly made of carbon in forms such as graphite and potentially diamond. The transformation of carbon into diamond on 55 Cancri e begins deep within the planet, where temperatures are sufficient to melt carbon. Under the immense gravitational pressure of the planet, molten carbon gradually crystallizes into diamond. This process mirrors diamond formation on Earth, but occurs on a larger scale and at much higher temperatures. On our planet, diamonds form deep below the surface over billions of years under high temperature and pressure conditions, typically around 150 kilometers below ground. Conversely, on 55 Cancri e, this process is accelerated by the planet's extreme environment, potentially resulting in a surface layer largely composed of diamond. This hypothesis is bolstered by observations of 55 Cancri e's density, and its parent star's carbon-rich nature. The planet's exceptionally high density indicates it is not composed of lighter elements like hydrogen and helium, as seen in many gas giants, but instead of heavier elements such as carbon. Coupled with the carbon abundance observed in its star, scientists posit that 55 Cancri e might indeed be a diamond world. The discovery of valuable materials like diamonds on planets such as 55 Cancri e provides profound insights into the diverse processes of planet formation and the varying conditions found across our universe. This revelation highlights the vast range of compositions and characteristics that planets can exhibit, illustrating the incredible diversity of planetary systems beyond our own. This diversity stems from the availability of materials in the regions where planets form around their host stars. For instance, 55 Cancri e's abundance of carbon, relative to other elements, suggests that its formation region was enriched in carbon-based compounds. This is in contrast to Earth, where silicon and oxygen predominate, resulting in a rocky surface. The presence of a diamond-rich planet indicates that the protoplanetary disk from which it originated had a distinct chemical composition, underscoring the influence of stellar and molecular cloud environments on shaping emerging planets. The transformation of these materials under extreme conditions, such as high pressure and temperature leading to diamond formation, provides valuable insights into the internal processes and thermal dynamics of these distant worlds. It implies that planets can possess internal heat and pressure mechanisms vastly different from those found on Earth, opening new avenues for research in planetary geophysics and chemistry. Understanding how planets with surfaces rich in valuable materials form also enhances our knowledge of the life cycles of stars and planetary systems. It hints at the evolutionary trajectories that planetary systems might follow, and the long-term fate of planets over billions of years. For example, a planet rich in carbon may evolve differently over time compared to a planet abundant in water or a gas giant, influencing its surface conditions, atmosphere, and potential to harbor diverse forms of life. The rings of J1407b, an exoplanet located hundreds of light-years away from Earth, represent a breathtaking discovery in the field of exoplanetary science. These rings are not only expansive but also extraordinarily vast, surpassing anything found within our own solar system. To grasp their scale, consider that J1407b's rings are so immense that they could encircle Saturn's rings over 200 times. Saturn's rings, already a wonder of our solar system, pale in comparison to the sheer size of J1407b's ring system. Spanning nearly 90 million kilometers, about 56 million miles in diameter, J1407b's rings highlight the remarkable diversity of planetary systems across the universe. Their discovery provides astronomers with a captivating opportunity to study planetary formation dynamics and the complexities of ring systems. Composed of ice, rock particles, and possibly moonlets or smaller bodies orbiting the planet, similar to Saturn's shepherd moons, these rings offer clues about the planet's past. The colossal expanse of J1407b's rings suggests they could be remnants of a colossal collision or the early stages of moon formation, offering insights into processes that may have occurred during the early solar system, but on a much larger scale. Analogous to Saturn's rings, which have demonstrated how moons can form within a planet's ring system, the particles within J1407b's rings interact under the planet's gravitational influence, potentially forming moonlets that could evolve into larger moons over time. The theory suggests that as particles within J1407b's vast rings collide and adhere to one another, they gradually aggregate into larger objects over time. These growing objects may eventually accrue enough mass to clear their orbits within the ring, a crucial step in their transformation into fully formed moons. This intricate process, though gradual and complex, provides a compelling window into planetary science, offering insights into the potential formation mechanisms of moons and other small bodies within our solar system. The emergence of moons within the expansive rings of J1407b holds profound implications for our comprehension of planetary systems and the dynamics of ring structures. Studying this phenomenon provides valuable opportunities to gather data on the conditions conducive to moon formation, the timelines involved in this evolutionary process, and how newly formed moons might influence the overall structure and stability of their parent rings. Ogle 2005 BLG 390 LB, located approximately 21,500 light-years away in the constellation of Sagittarius, has earned the classification of an iceball planet due to its frigid surface temperatures and distant orbit from its parent star. This distant positioning places it far beyond Earth's distance from the Sun, resulting in minimal warmth reaching the planet. Described as an iceball, Ogle 2005 BLG 390 LB exhibits surface temperatures estimated around -220 degrees Celsius, -364 degrees Fahrenheit, cold enough to keep water permanently frozen across its entire landscape. This characterization stems from its thermal properties and environmental conditions. Unlike ice giants in our solar system, such as Uranus and Neptune, which possess thick atmospheres rich in hydrogen and helium, an iceball planet like Ogle 2005 BLG 390 LB is believed to feature a solid, icy surface. Its extreme cold is primarily due to its distant orbit, which limits the amount of solar energy it receives, preventing its surface from warming above the freezing point of water. This classification underscores the vast range of planetary environments present in our universe. Iceball planets challenge our notions of habitability and the conditions necessary for life. While the severe cold on such planets seems inhospitable to life as we understand it, studying these celestial bodies provides valuable insights into the extreme climates that can exist on planets and their potential for hosting water in its various forms across different cosmic bodies. In planetary science, a planet's temperature is a critical factor shaping its atmosphere. Ogle 2005 BLG 390 LB, being extremely cold, faces unique atmospheric challenges. Volatile compounds like water vapor, carbon dioxide, and methane, which would normally form gases on warmer planets, freeze out on its surface as snow or ice. This process significantly thins and reduces the density of its atmosphere, as fewer gases remain in a vapor state to create a substantial atmospheric layer. The lack of a thick atmosphere on Ogle 2005 BLE 390 LB means that any heat from its star or internal sources is not effectively retained, intensifying its already cold conditions. In contrast, planets with thicker atmospheres, rich in greenhouse gases, can trap heat and maintain relatively warmer temperatures, even at great distances from their stars. The temperature and atmospheric conditions of Ogle 2005 BBLG 390 LB provide insights into its potential to support life as we understand it. The absence of a substantial atmosphere and the extreme cold make it unlikely for liquid water to exist on its surface, a crucial requirement for life as we know it on Earth. However, these harsh conditions spark curiosity about the possibility of extremophile life forms adapted to such extreme environments, challenging our understanding of habitability in the universe. Researching distant and cold planets like Ogle 2005 BLG 390 LB, located thousands of light-years away, involves advanced astronomical techniques and technologies. Scientists utilize observational methods and theoretical models to unravel the mysteries of these distant worlds. Gravitational microlensing is a key technique used to detect and study planets like Ogle 2005 BLG 390 LB. This phenomenon occurs when the gravity of a foreground star or planet bends and magnifies the light from a background star, revealing the presence of planets orbiting the foreground star and providing details about their mass and distance from their host star. Gravitational microlensing is a powerful method for detecting distant and faint exoplanets that are difficult to observe using traditional techniques like transit observations or direct imaging. This method is particularly effective for finding cold iceball planets such as Ogle 2005 BLG 390 LB. Unlike other methods, microlensing does not rely on the planet or its host star emitting light. Instead, it detects planets by observing how their gravity bends and magnifies the light from a background star. This approach is highly sensitive to low-mass planets and can detect them across a wide range of distances from their host stars. In conjunction with gravitational microlensing, scientists employ sophisticated computer models and simulations to study these distant planets. By inputting known physical parameters such as the planet's mass, distance from its star, and orbital characteristics, researchers can simulate conditions on the planet's surface and atmosphere. These models provide valuable insights into the planet's temperature, atmospheric composition, and potential for hosting water or ice. To confirm and further investigate microlensing detections, telescopes equipped with sensitive instruments, both on the ground and in space, are essential. These telescopes gather additional data about the star system, refining measurements and validating the presence of the detected planet. While directly observing the atmosphere or surface of such distant planets remains challenging, the combined use of microlensing and follow-up observations offers scientists significant knowledge about these remote celestial bodies. Kelt 9b holds the distinction of being the hottest known exoplanet, owing to a combination of extreme factors that create its blistering conditions. Situated approximately 670 light-years away in the constellation Cygnus, Kelt 9b orbits its host star Kelt 9, which is exceptionally hot, nearly twice as hot as our Sun. This stellar proximity is key, with Kelt 9b completing an orbit in just about 1.5 Earth days, placing it in a tremendously close and intense stellar environment. Due to its close orbit around Kelt 9, Kelt 9b receives thousands of times more radiation than planets in our solar system receive from the Sun. This intense radiation heats the planet's atmosphere to over 4,300 degrees Celsius, 7,800 degrees Fahrenheit, hotter than many stars and well beyond the melting points of most materials found on Earth. These extreme temperatures foster unique atmospheric chemistry, potentially leading to vaporized metals and the destruction of molecular hydrogen, typically abundant in other gas giants' atmospheres. Additionally, Kelt 9b lacks a significant reflective atmosphere that could moderate its temperatures. The absence of reflective clouds or ice allows the planet to absorb a maximum amount of stellar radiation, further elevating its already scorching surface temperatures. The planet's tidally locked rotation, where one side always faces the star and the other remains in perpetual darkness, exacerbates these extremes. Despite potential heat distribution by atmospheric winds, the day side of Kelt 9b remains infernally hot, providing a striking example of the extreme conditions that exoplanets can experience. For Kelt 9b, the hottest known exoplanet, upcoming observations aim to delve deeper into its remarkable atmosphere and the extreme conditions created by its proximity to its host star, Kelt 9. Astronomers are eager to leverage the next generation of space and ground-based telescopes to explore this intriguing world in greater detail. A primary objective is to scrutinize Kelt 9b's atmospheric composition, particularly identifying exotic molecules and vaporized metals that exist due to its scorching temperatures, substances that may be rare or unknown in cooler planetary atmospheres. Another critical focus of future observations is investigating Kelt 9b's atmospheric dynamics and weather patterns. The stark temperature contrasts between its day and night sides present an opportunity to uncover unprecedented insights into extreme weather phenomena, potentially unlike anything observed in our solar system. Advanced instruments such as the James Webb Space Telescope, JWST, and the Extremely Large Telescope, ELT, are poised to play pivotal roles in these endeavors. The JWST's infrared sensitivity will enable detailed measurements of Kelt 9b's thermal emissions, offering crucial data on temperature distribution and atmospheric makeup. Meanwhile, the ELT's superior resolution will provide unprecedented views of the planet's atmospheric chemistry. Additionally, future observations will seek to investigate Kelt 9b's magnetic field and its interaction with the stellar wind from Kelt 9. Understanding this interaction is essential for comprehending atmospheric loss processes and their impact on the planet's long-term evolution and stability. The extreme seasonal variations on HD 80606b, a gas giant exoplanet located approximately 190 light-years away in the constellation Ursa Major, stem from its highly eccentric orbit around its host star. Unlike the nearly circular orbits of planets in our solar system, HD 80606b follows a highly elongated path that brings it very close to its star at Periastron, the closest point in its orbit, and then swings it far away at Apastron, the farthest point. This unique orbital setup results in dramatic fluctuations in temperature and weather patterns on the planet throughout its orbit, which lasts about 111 days. During Periastron, when HD 80606b approaches its star closely, it undergoes rapid and extreme heating due to intense solar radiation. Within hours, the planet's atmosphere can heat up by hundreds of degrees, a phenomenon unseen in our solar system. This rapid temperature increase drives powerful weather phenomena like supersonic winds and expansive storm systems that can envelop the entire planet. This contrasts sharply with the much cooler and calmer conditions experienced at Apastron, when HD 80606b is farthest from its star. The degree of these seasonal changes is further influenced by the planet's rotation and its orbital tilt. If HD 80606b is tidally locked, with one side permanently facing the star, the contrast between its scorching day side and frigid night side would be accentuated. However, even if the planet rotates, the swift heating and cooling as it traverses its eccentric orbit would still lead to significant seasonal variations. Astronomers employ diverse methods such as transit observations and radial velocity measurements to study the extreme seasonal variations of HD 80606b. These techniques involve observing the planet as it passes in front of its star from our viewpoint and monitoring the star's motion caused by the planet's gravitational pull. Through these observations, scientists gain insights into the dynamics of HD 80606b's atmosphere and how its eccentric orbit influences its climate. The pronounced seasonal changes on HD 80606b, driven by its highly eccentric orbit, hold significant implications for its potential habitability. The planet experiences dramatic shifts in temperature and weather conditions, ranging from extreme heat to relatively cooler phases, which present challenges for the emergence and sustainability of life as we know it. During Periastron, the planet's closest approach to its star, the atmosphere can rapidly heat up by hundreds of degrees in mere hours, creating harsh conditions unsuitable for life. Habitability typically hinges on a stable environment where liquid water can persist on a planet's surface, an essential condition for life. However, on HD 80606b, the extreme temperature swings make it unlikely for liquid water to remain stable. Near Periastron, any surface water would likely evaporate due to the intense heat, while at Apastron, the coldest point in its orbit, any remaining water could freeze solid. The planets circling the pulsar PSRB 1257+12 present a fascinating and unexpected find in astronomy, challenging our notions of planetary formation. Pulsars are neutron stars with intense magnetic fields that emit electromagnetic radiation from their poles as they spin. This radiation sweeps past Earth like a beacon detectable by radio telescopes. Located approximately 2,300 light-years away in the Virgo constellation, PSRB 1257+12. Stunned astronomers by hosting planets, this discovery was groundbreaking because it showcased planets existing in a vastly different setting compared to our solar system. What sets these planets apart is not just their orbit around a pulsar, but also the unique conditions they endure. Pulsars are the remnants of massive stars that have undergone supernova explosions, leaving behind an incredibly dense core composed mainly of neutrons. These neutron stars possess intense magnetic fields and emit high levels of radiation, creating an extremely harsh environment unsuitable for life as we know it. The discovery of planets around pulsars poses intriguing questions about how these planets formed and continue to exist. Traditional theories of planet formation, which involve the gradual accumulation of dust and gas in a protoplanetary disk around a young star, don't straightforwardly apply to the surroundings of a neutron star. Such material would likely have been dispersed by the supernova explosion that formed the pulsar. The planets orbiting PSRB 1257+12 were first identified in the early 1990s and are primarily terrestrial in mass. Their detection marked a significant advancement in exoplanetary science, achieved through precise measurements of the pulsar's pulse timing. As these planets orbit the pulsar, their gravitational influence causes slight variations in the timing of its pulses, a unique method for detecting exoplanets associated with pulsars. The formation of these pulsar planets presents another fascinating puzzle. One hypothesis proposes that they could have originated from the debris left behind by the supernova, indicating a potential second round of planet formation. Alternatively, these planets might have been pre-existing bodies captured by the pulsar's gravitational pull or remnants of a star system that managed to survive the supernova explosion in some capacity. The discovery of planets orbiting PSRB 1257+12 marked a significant breakthrough in exoplanetary research, demonstrating that planets can form and endure in extreme and previously thought inhospitable environments. The conditions on these pulsar-orbiting planets stand in stark contrast to those found in our solar system, presenting an environment that is nearly unparalleled. Our solar system's planets orbit a stable main sequence star, the Sun, which provides a steady source of light and heat crucial for sustaining life on Earth and influencing the climate and atmospheric processes on other planets. In contrast, the planets orbiting PSRB 1257+12 circle. A pulsar, an extraordinarily dense remnant of a supernova explosion emitting intense electromagnetic radiation and possessing formidable magnetic fields. The radiation environment surrounding a pulsar is exceedingly harsh compared to the sunlight that bathes our solar system. Pulsar radiation can strip away atmospheres, irradiate surfaces, and potentially sterilize planets, rendering them inhospitable for life as we understand it. In our solar system, planets like Earth benefit from protective magnetic fields that shield them from solar wind and cosmic rays, safeguarding their atmospheres and enabling conditions conducive to life. Conversely, the planets orbiting PSRB 1257+12 lack such protection, suggesting any atmosphere they may possess could be minimal or absent altogether. The process of planet formation around a pulsar differs significantly from that in our solar system. While our solar system's planets coalesced from a protoplanetary disk of gas and dust surrounding the young Sun, the planets around PSRB 1257+12 likely formed from the remnants of the supernova that produced the pulsar. This suggests a distinct second phase of planet formation, potentially involving different materials and mechanisms compared to those that shaped our solar system's planets. Temperature conditions also illustrate a striking contrast. In our solar system, planets experience temperatures suitable for liquid water on Earth and icy environments on outer planets, driven by the Sun's consistent energy output. In contrast, planets orbiting PSRB 1257+12 likely endure extreme temperature fluctuations influenced by their proximity to the pulsar and its intense emissions. These conditions diverge significantly from the stable environments observed in our solar system, where varying climates and atmospheric dynamics are supported by the Sun's radiation. CoRoT 2b, an exoplanet discovered by the CoRoT space mission, provides a compelling example of a planet influencing its host star in observable ways from Earth. This hot Jupiter orbits CoRoT 2 every 1.7 days, positioned very close to its star. This close proximity results in significant interactions between the planet and its host star, revealing dynamic processes between stars and their planets. One notable effect of CoRoT 2b on its host star is star-planet interaction. The strong gravitational pull of CoRoT 2b can trigger activity in the star's outer layers, potentially increasing magnetic activity such as star spots and flares. This phenomenon draws parallels to how the Moon affects Earth's tides, but operates on a larger scale, involving magnetic fields and stellar plasma. The close orbit of CoRoT 2b around its host star exposes it to intense stellar radiation, heating the planet's atmosphere to extreme temperatures. This thermal energy can cause the planet's atmosphere to expand and sometimes escape into space. As the atmosphere escapes, it forms a cloud of material around the planet that interacts with the star. This interaction can lead to a transfer of angular momentum from the planet to the star, influencing the star's rotation rate and magnetic field. The CoRoT system presents another fascinating dimension: the potential for the planet to induce chemical changes in its host star's outer layers. As material from CoRoT-B's atmosphere escapes, it may accrete onto the star, altering its chemical composition and spectral characteristics. This process, called accretion, allows astronomers to infer details about the planet's atmosphere by studying changes in the star's spectrum. Astronomers employ spectroscopy to examine these interactions, analyzing the star's light to detect variations in brightness, magnetic activity, and chemical makeup. Observations of the CoRoT system contribute significantly to our understanding of how planets influence their host stars, providing insights into the evolution of planetary systems and the intricate dynamics that govern their interactions. The interaction between CoRoT-B and its host star, CoRoT-A, underscores the complex relationships between stars and planets, expanding our comprehension of the cosmic interplay throughout the universe. These interactions demonstrate that planets, particularly those in close orbits like hot Jupiters, can profoundly impact their stars, influencing magnetic behavior, rotation rates, and even the chemical compositions of their host stars. This perspective contrasts sharply with the traditional belief that stars unilaterally determine the conditions of their orbiting planets without reciprocal effects. The phenomenon of star-planet interaction, exemplified by the CoRoT system, reveals that planets can induce magnetic disturbances in their host stars, triggering heightened stellar activity like flares and spots. This discovery is significant because it suggests that planets' presence and characteristics can directly influence the stellar environment, altering the conditions that govern these celestial bodies' existence and evolution. In the case of CoRoT-B, its close orbit around the host star and the resulting gravitational forces illustrate how a planet's influence can extend beyond its own atmosphere, impacting the star itself. These interactions underscore the potential for atmospheric loss from planets exposed to intense stellar radiation. The process of a planet losing its atmosphere and potentially transferring material to the star establishes a mutual exchange between stars and planets, blurring the boundaries of their relationships. This exchange can lead to changes in the chemical composition of the star's outer layers, offering astronomers indirect means to study exoplanet atmospheres through observations of their host stars. The intriguing phenomenon of gemstone rain on HAT P7b, an exoplanet located approximately 1,040 light-years away, highlights its unique atmospheric dynamics shaped by extreme conditions on this gas giant. HAT P7b belongs to the category of hot Jupiters, similar in size to Jupiter but much closer to its host star, resulting in extraordinarily high temperatures. The precipitation of materials like rubies and sapphires in its atmosphere is attributed to the presence of aluminum oxide. Under terrestrial conditions, aluminum oxide crystallizes into corundum, the mineral base for gems such as rubies and sapphires, depending on trace impurities. The scorching temperatures on HAT P7b's day side facilitate the formation of aluminum oxide vapor in its atmosphere. Orbiting so close to its star subjects the planet to intense stellar radiation, heating the atmosphere to temperatures where metals can vaporize and chemical reactions can occur. As the vapor moves with strong winds to the cooler night side, the temperature drop allows the aluminum oxide to condense into clouds. Further cooling may lead to the precipitation of corundum crystals, which could resemble rubies and sapphires depending on local conditions, such as the presence of trace elements like chromium or iron. This phenomenon poetically describes gemstone rain on HAT P7b. This extraordinary weather phenomenon underscores the fascination of studying exoplanets, offering insights into the diverse environmental conditions beyond our solar system. Researchers study HAT P7b's atmospheric dynamics, including gemstone rain, through variations in its brightness and spectral analysis. These observations reveal details about the planet's atmospheric composition and temperature distribution, advancing our understanding of planetary science and the complexities of hot Jupiter climates. The remarkable occurrence of iron rain on WASP-76b, situated approximately 640 light-years away in the Pisces constellation, arises from the extreme temperature differentials and unique atmospheric dynamics of this ultra-hot Jupiter. WASP-76b orbits very close to its host star, completing an orbit in just 1.8 Earth days, exposing its day side to intense stellar radiation. Daytime temperatures exceed 2,400 degrees Celsius, about 4,350 degrees Fahrenheit, sufficient to vaporize metals like iron. The process of iron rain begins with iron vaporizing on the scorching day side of the planet. This vapor is then transported by atmospheric currents to the cooler night side, where temperatures drop significantly. As the vapor cools, it condenses into droplets, forming clouds that precipitate as iron rain. This stark temperature disparity between the day and night sides, coupled with efficient atmospheric circulation, creates the ideal conditions for this metallic precipitation. Studies of WASP-76b, particularly using spectroscopy, have confirmed this phenomenon. Spectroscopic analysis enables astronomers to identify the chemical compositions of planetary atmospheres by examining the starlight filtered through them. The presence of iron vapor on the day side and its absence on the night side indicates that the iron condenses and precipitates as rain before it can cycle back to the day side. TOI 700D, discovered by NASA's TESS mission, has drawn significant interest from scientists and space enthusiasts alike due to its potential habitability. Situated approximately 100 light-years away in the Dorado constellation, TOI 700D orbits a small, cool M-dwarf star as the outermost planet in its system. What distinguishes TOI 700D as a promising candidate for habitability are several key characteristics, setting it apart from many other exoplanets. Crucially, TOI 700D resides within its star's habitable zone, an orbital region where conditions may be conducive for liquid water to exist on the planet's surface, a fundamental prerequisite for life as we understand it. Its orbit places it at a distance where it receives a comparable amount of stellar energy as Earth does from the Sun, implying temperatures on TOI 700D could support liquid water, given the presence of an appropriate atmosphere. Moreover, TOI 700D is roughly Earth-sized, with estimates suggesting it has a radius about 1.2 times that of Earth. This similarity in size suggests a rocky composition akin to Earth, Mars, and Venus, enhancing its potential to maintain a stable atmosphere, a critical factor for habitability. An atmosphere could not only supply essential gases for life, but also regulate the planet's temperature by trapping heat through greenhouse effects. TOI 700D's orbit is tidally locked to its star, resulting in one side of the planet always facing the star, the day side, while the other side remains in perpetual darkness, the night side. This arrangement typically leads to drastic temperature differences between the two hemispheres. However, the presence of an atmosphere could mitigate these extremes by redistributing heat, potentially stabilizing the climate enough to sustain liquid water and possibly life. TOI 700, the host star of TOI 700D, belongs to the category of quiet M dwarfs, known for exhibiting fewer solar flares compared to other stars of similar type. Solar flares can erode a planet's atmosphere and subject its surface to harmful radiation, factors that can hinder habitability. The relatively tranquil behavior of TOI 700 enhances the prospects for TOI 700D's habitability by reducing these risks. LHS 3844b, an exoplanet orbiting a red dwarf star about 48.6 light-years away in the constellation of Indus, exhibits extreme temperature disparities between its day and night sides due to its close proximity to its host star and its apparent lack of a substantial atmosphere. This terrestrial planet completes an orbit around its star in just 11 hours, positioning it much closer than Earth is to the Sun. This proximity results in the planet receiving intense stellar radiation on its day side, leading to extremely high temperatures. The primary factor driving the stark temperature contrast on LHS 3844b is its tidally locked orbit. Tidal locking means one side of the planet always faces the star, experiencing perpetual daylight, while the opposite side remains in continuous darkness. In the absence of an atmosphere to redistribute heat, the day side becomes intensely hot, while the night side remains significantly cooler due to the absence of direct stellar heating. Studies using instruments like NASA's Spitzer Space Telescope suggest that LHS 3844b likely lacks a substantial atmosphere. An atmosphere plays a crucial role in regulating a planet's climate by distributing heat. For instance, Earth's atmosphere helps moderate global temperatures by transferring heat from equatorial regions to the poles. The absence of such an atmosphere on LHS 3844b means that heat from its star isn't effectively distributed across the planet. Consequently, temperatures on the day side of LHS 3844b can soar to around 800 degrees Celsius, approximately 1,472 degrees Fahrenheit, while the night side experiences a substantial drop in temperature due to the lack of direct sunlight. Gliese 1214b is classified as a super-Earth because it is an exoplanet larger than Earth, but smaller than the ice giants Uranus and Neptune. It possesses a mass about 6.5 times that of Earth and a radius approximately 2.7 times larger, placing it squarely within the category of super-Earths. The significance of this classification lies in the range of potential characteristics Gliese 1214b could exhibit, including a dense atmosphere, the presence of liquid water, or even an ocean-dominated surface, depending on its composition and atmospheric conditions. However, the term super-Earth does not imply that the planet is necessarily habitable or Earth-like in terms of its climate and environment. Rather, it denotes its size relative to Earth and suggests a diversity of planetary types beyond our solar system. Super-Earths like Gliese 1214b captivate astronomers because they represent a planetary class absent in our own solar system. They offer unique opportunities to study planetary formation, evolution, and the potential for life under conditions distinct from those found on Earth. Gliese 1214b orbits a red dwarf star located approximately 48 light-years away in the constellation Ophiuchus. Its close proximity to its host star, resulting in a short orbital period of about 38 hours, significantly influences the planet's temperature and atmospheric dynamics. Observations indicate that Gliese 1214b possesses a substantial atmosphere, potentially rich in water vapor or other heavy molecules. This characteristic has sparked interest in understanding its surface conditions, including the possibility of hosting an exotic form of water under extreme pressure and temperature, a concept known as a water world. Studying Gliese 1214b alongside other super-Earths is pivotal for advancing our understanding of the diverse array of planets throughout the cosmos. Scientists employ sophisticated techniques such as transit spectroscopy to analyze the atmospheres of these distant worlds. This method provides valuable insights into their chemical compositions, weather patterns, and the potential suitability for life as we know it. Such research not only expands our knowledge of exoplanetary systems, but also refines models of planetary formation under diverse environmental conditions. Proxima Centauri b orbits the closest star to the Sun, Proxima Centauri, located approximately 4.2 light-years away in the constellation of Centaurus. It stands out as a leading candidate in the search for extraterrestrial life due to several compelling attributes. Chief among these is its position within the habitable zone of its star, often referred to as the Goldilocks zone. This zone denotes the range of distances from a star, where conditions could potentially support liquid water on a planet's surface, a crucial requirement for life as we understand it. Proxima Centauri b's orbit within this zone suggests it could maintain surface temperatures conducive to liquid water, provided it possesses a suitable atmosphere. Another key factor supporting Proxima Centauri b's candidacy for hosting life is its Earth-like size. Estimates indicate the planet is at least 1.17 times the mass of Earth, indicating a rocky composition rather than a gaseous one. This similarity in size and composition increases the likelihood that Proxima Centauri b may harbor Earth-like environmental conditions, further bolstering its potential for habitability. The planet's proximity to Earth presents a unique advantage for scientific observation and study. As the closest known exoplanet, Proxima Centauri b is a prime target for future missions and telescopes designed to examine exoplanetary atmospheres, surface features, and potential signs of life. Advanced technologies, including upcoming instruments like the James Webb Space Telescope, offer the promise of analyzing the planet's atmospheric chemistry, searching for water, and detecting molecules that could hint at biological activity. While Proxima Centauri b holds promise as a potential haven for extraterrestrial life, there are notable challenges to its habitability. Orbiting Proxima Centauri, a red dwarf star known for frequent stellar flares and high levels of activity, the planet faces significant radiation exposure. These factors could jeopardize its atmosphere and surface conditions, essential for supporting life as we understand it. For Proxima Centauri b to sustain life, it would likely require a robust magnetic field capable of shielding it from the star's intense radiation and preserving its atmosphere. Despite these challenges, Proxima Centauri b remains a leading candidate in the search for alien life due to its placement within the habitable zone of its star, its Earth-like size, and its status as the closest exoplanet to our solar system. Scientists are eager to explore Proxima Centauri b further through future observations, which could provide crucial insights into its potential for hosting life beyond Earth. Kepler-22b, discovered by NASA's Kepler Space Telescope, has captured significant attention within the scientific community for its potential to support life. Positioned approximately 620 light-years away in the constellation of Cygnus, this exoplanet orbits within the habitable zone of its star, Kepler-22. This zone is crucial because it encompasses distances where conditions might permit liquid water to exist, a fundamental requirement for life as we understand it. The primary allure of Kepler-22b lies in its location within this habitable zone. This positioning suggests that the planet receives a comparable amount of stellar radiation to Earth from the Sun, potentially fostering a climate suitable for liquid water on its surface. Liquid water is vital for biochemical processes essential to sustain life. Moreover, Kepler-22b boasts a radius approximately 2.4 times larger than Earth, classifying it as a super-Earth. While uncertainties remain regarding its exact mass and composition due to current observational constraints, there is speculation that Kepler-22b could possess either a rocky surface or a global ocean covering its entirety. The concept of a world entirely covered by liquid water, devoid of exposed land, presents intriguing possibilities for supporting aquatic life forms. The star Kepler-22 plays a crucial role in assessing the potential habitability of its orbiting exoplanet, Kepler-22b. It belongs to the G-type category, akin to our Sun, but slightly smaller and cooler. G-type stars like Kepler-22 are considered favorable for life's development due to their stable and enduring energy output. This consistency contrasts with more volatile stars such as red dwarfs, which are prone to intense flaring. The stable stellar environment of Kepler-22 suggests that Kepler-22b may maintain a stable atmosphere, a critical factor for supporting life. However, the planet's ability to host life depends not only on its location within the habitable zone, but also on its atmospheric composition, which remains uncertain. An ideal scenario would involve an atmosphere capable of trapping heat through a greenhouse effect without leading to excessive warming or becoming inhospitable to life. Future observations, possibly through advanced telescopes like the James Webb Space Telescope, hold promise for unveiling the composition of Kepler-22b's atmosphere. These observations could reveal gases indicative of biological processes, providing key insights into the potential habitability of this distant world and advancing our understanding of planetary environments beyond our solar system. Discovered in 2009, WASP-17b stands out in the realm of exoplanets due to its extraordinary characteristics, earning it the nickname the Backwards Giant. Located roughly 1,000 light-years away in the constellation Scorpius, this gas giant boasts a radius nearly twice that of Jupiter, while only possessing half its mass. This results in an unusually low density, likening it to a celestial puffball in space. What truly distinguishes WASP-17b is its retrograde orbit, moving in the opposite direction to its host star's rotation, a rarity among exoplanets. This backward motion challenges conventional theories of planetary formation and migration. Typically, planets form from a rotating disk of gas and dust, aligning their orbits with their star's rotation. WASP-17b's retrograde orbit suggests a turbulent history involving gravitational interactions with other celestial bodies or nearby stars, potentially leading to significant alterations in its original orbit. These interactions could include gravitational slingshots from close encounters with other planets, or more gradual processes like Kozai cycles, which can transform a planet's orbital inclination over time, potentially flipping its orbit relative to its star. WASP-17b's atmospheric properties also intrigue scientists. Observations hint at the presence of water vapor and possibly carbon monoxide, yet its extended atmosphere and low density pose questions about its composition and weather dynamics. The intense radiation it receives due to its proximity to the host star could drive extreme atmospheric phenomena not seen in our own solar system. Located approximately 560 light-years away in the constellation Draco, Kepler-10b orbits its host star, Kepler-10, at an extraordinarily close distance, completing a full orbit in less than 20 hours. This close proximity exposes Kepler-10b to extreme temperatures, leading to its nickname, the roasting rocky world. The intense radiation from its host star heats Kepler-10b's surface to over 1,300 degrees Celsius, about 2,372 degrees Fahrenheit, hot enough to melt iron and rock, resulting in a landscape covered in molten lava. While these conditions make Kepler-10b inhospitable for life as we know it, they provide a unique opportunity to study the compositions and atmospheres of rocky exoplanets and the environments in which they form and evolve. Kepler-10b is predominantly composed of silicate rock, with a mass about 3.3 times that of Earth and a radius 1.47 times larger than our planets. These characteristics classify it as a terrestrial or rocky planet akin to Earth, Venus, Mars, and Mercury in our own solar system. However, its close orbit and resulting extreme temperatures underscore the diversity of planetary environments within our galaxy. The discovery of Kepler-10b was significant not only for confirming the existence of rocky exoplanets, but also for showcasing the capabilities of the Kepler telescope and the transit method of detecting exoplanets. By observing the slight dimming of a star's light as a planet passes in front of it, astronomers glean essential details about the planet's size, density, and orbital characteristics. For Kepler-10b, these observations have yielded crucial insights into rocky planets' properties, shedding light on their compositions and structures. Kepler-10b's close proximity to its host star raises intriguing questions about its formation and history. It likely formed farther out in its solar system and migrated inward over time, possibly through interactions with other planets or the protoplanetary disk from which it originated. Understanding these dynamic processes is vital for unraveling the complexities of planetary systems, including our own. Situated approximately 33 light-years away in the constellation Leo, Gliese 436b has captivated astronomers with its paradoxical nature since its discovery. Dubbed the Burning Ice Planet, it challenges conventional ideas about planetary conditions and composition. Despite its close orbit around its host star, Gliese 436, completing a swift orbit in just over 2 days, the planet's surface is covered in a peculiar substance known as hot ice, a form of water existing under immense pressure and high temperatures. Gliese 436b boasts surface temperatures exceeding 400 degrees Celsius, 750 degrees Fahrenheit, conditions where water would typically exist as steam. However, the planet's intense gravitational forces compress water into an exotic variant called Ice-X. Unlike normal ice, Ice-X remains solid even at elevated temperatures due to the extreme pressure, creating a scenario where ice can endure in a near-stellar environment. This unique state of matter on Gliese 436b arises from its distinctive atmospheric and physical traits. The planet's hydrogen and helium-rich atmosphere, coupled with traces of water vapor, indicate the presence of water under extreme conditions. Instead of conventional forms, these conditions transform water into hot ice and supercritical fluid. a hybrid state blending liquid and gas properties. The discovery of Gliese 436b has profoundly enriched our comprehension of exoplanetary diversity and the array of survivable conditions. It challenges assumptions about water's behavior and the environmental prerequisites for various states of matter. The presence of hot ice on Gliese 436b hints at the potential existence of numerous planets with similarly unconventional environments, expanding our understanding of planetary diversity across the universe. Situated approximately 150 light-years away in the constellation Pegasus, HD 209458b, nicknamed OSIRIS, stands as a remarkable example among exoplanets due to its striking process of evaporation. This gas giant orbits its host star at a mere eighth of the distance between Earth and the Sun, resulting in surface temperatures surpassing 1,000 degrees Celsius, about 1,832 degrees Fahrenheit. Such close proximity subjects HD 209458b to intense stellar radiation, heating its atmosphere to the point where it expands and begins to escape into space. The phenomenon of atmospheric escape observed on HD 209458b was one of the earliest instances detected directly. Utilizing the Hubble Space Telescope, astronomers observed hydrogen, carbon, and oxygen being ejected from the planet at speeds reaching thousands of kilometers per hour, forming a vast, trailing tail of material akin to a comet. This escape process is so significant that it is estimated the planet loses between 100 million to 500 million kilograms of mass per second. The evaporation of HD 209458b offers crucial insights into the dynamic interactions between exoplanets and their host stars, especially in cases of planets in close orbits. The intense radiation driving atmospheric escape on OSIRIS also ionizes the escaping gases, which interact with the star's light, creating observable signatures that led to the discovery of this phenomenon. Space is a vast expanse filled with galaxies and planets, each holding mysteries that are both captivating and unsettling.